Good day. My name is Derrel Martin. I'm a professor in biological systems engineering, working in irrigation and water resources engineering. And I want to visit with you today about the water resource management in the state of Nebraska. We'll take a little look at the water resources that are available in the state, some of the issues that are driving changes in irrigation management, both from the water quantity side primarily, but a little bit on water quality as well. If we start here by looking at this particular map, shows the amount of land that was irrigated in each state in the United States in 2007. And what you'll see from this diagram is that Nebraska had become the most heavily irrigated state in the Union. You can see that we're at about 8.6 million acres in the 2007 survey. California was second with about 8 million acres. And so we've become the most widely irrigated state. We use center pivots more than any other state. And so that's really what a lot of our programs evolve around. This slide shows the changes in irrigated area across the nation and across Nebraska over about the 15-year period from 1997 to 2012. And you can see the blue bars are showing that the amount of land irrigated in the United States has remained about the same over that time period, about 55 to 56 million acres of land irrigated. Nebraska has went up a little bit over that time period, went from about 7.1 million acres to about 8.6 in 2007. The numbers that are shown in these surveys are a little bit lower in 2012 than they were in 2007. We're not quite sure why there's that anomaly there. It may have been that this survey was based on data from 2012, which was actually a dry year and maybe some land wasn't irrigated. But today we're somewhere around 8.5 million acres plus or minus in terms of the amount of land we irrigate in the state. What that shows is that in Nebraska then, about 15% of the land that's irrigated in the United States is actually in the state of Nebraska. So, we're a major player when it comes to looking at irrigation and water management. Now, in the end, the main driver for any of these systems in the Great Plains is going to be the amount of precipitation that we have. So that's really our source of water. And so what this diagram shows is the variation in average annual rainfall as you progress across Nebraska. So we're by far the wettest in the southeast corner of the state. You can see that we're getting more than 34 inches of precipitation in this lower left, right corner. When we get out into the panhandle area, that precipitation drops down into that less than 16 inches. And so kind of a rule of thumb that we often use is that the average annual rainfall varies about 1 inch for every 25 miles that you go east or west across the state. So a lot of variation and a lot of differences in the hydrology as we go from the subhumid area in the east to the semi-arid area in the west. So it's certainly something to keep in mind when you look at weather reports that you see around the country. This looks at the way we irrigate, and when most of our land is irrigated with wells, pumping water from groundwater. And so this slide is showing the number of wells that were installed in each decade starting back in 1940. We really started developing irrigation in the 50s from groundwater. The issue really was we came out of World War II with some power equipment that we could use to lift and pump water. We also developed the ability to drill wells at that time, and in the early 50s was a time period of drought. And so there were kind of a perfect storm that aligned to have a lot of land developed. But as you can see here, the big decade was the 1970s that we put in almost 30,000 wells in that 10-year period. What was driving that was, again, there was a severe drought in the middle part of the 70s. Crop commodity prices were quite strong at that time. The center pivot, the patent on center pivots had just expired in 1969. And then there was also a federal tax incentive program that kind of encouraged the development of a lot of wells and groundwater in the 70s. Since that time, we've averaged somewhere around about 10,000 wells a decade. The decade here in the 2000 to 2010, we were actually about 14,000. And so far in the 5 years of this part of the decade, we're over that 5,000. One of these days we're going to stop putting in irrigation wells. I guess it's up for the public to decide where that limit should be. But this is kind of how we've developed that groundwater resource. This map is showing the location of new active irrigation wells since during the period 2000 to 2010. So what this is showing is the darker the green color, the more wells that were installed in that natural resources district. You can see that we installed about 13,000, a little over 13,000 new wells that were active for irrigation during that time period. A lot of that development occurred in the Central Platte Valley and in the northeast part of the state. Very little development, expansion of irrigated land or wells as you go west of about the middle or the 100th meridian in the state. We can also look at what happened then in the 5 years from 2010 to today. We put in about just under 7,000 new wells, and it's really the same story. Most of that development has occurred in the Platte Valley and up into the Loop and the Elkhorn and those regions. Very little development in the west and not much in the very southeast corner. So that's where we continue to develop irrigated wells in the state. Well, if we look at the impact of that pumping has had on our water resources, this is shown in this well-distributed map of groundwater level changes in Nebraska. So what this means is these areas in the map that are showing in a red color are areas where the water table has dropped since about 1950. We use 1950 as a reference point for the impact of well development because we had very few wells before 1950. And so what you can see is the two major areas where we have some declines of water levels are in the southwest corner, that Chase, Dundee, Perkins area, and then out in Box Butte County we have some areas where the water table has dropped a significant amount. There's some areas here in the east, in the Blues area, where there's been some changes of water level. This area tends to go up and down a little bit, kind of depending on how dry the decade was before the map was prepared. The blue areas in the map show locations where the water level has risen during that time period. And so what you'll see is most of those areas are associated with surface irrigation projects that divert water from the stream and deliver it to irrigated lands that are up away out of the area right next to the river. And so what has happened there is there's recharge from the canals, there's recharge from the irrigated land itself, and that water level is tended then to raise the water level over time. The main areas here we see are what we refer to as the Tri-County area out in the middle. There's some up in the Farwell, in that area up in the Loop, and some around the reservoirs like at McConaughey and at the Sutherland reservoirs. So those are areas where we've diverted stream water, we've irrigated with it, and some of that water went back into groundwater. And so we see areas where the water level has risen and areas where it has fallen over time. This is the same kind of picture looking now at the entire High Plains, or you might call it Okolala Aquifer. And what this is showing is that these areas here in red, that the darker the red, the more the water level has declined since about that same time. Now, it's a little hard to read the numbers here, but what this shows is those most severe areas of declines have been here in the panhandle of Texas and up in southwest Kansas, where the water level may have dropped over 100 feet in those locations. When we look at Nebraska or northern Kansas, the northern Great Plains, those declines of water levels have been less severe in our region than they have in the southern plains. To really take a look at this story, though, we have to think about how much water is available in those aquifers in those different locations. There's very little flow of water from, say, Nebraska into Kansas or Kansas into Texas. And so the groundwater is very local. It doesn't flow very fast. Groundwater flows maybe 300 to 400 feet a year on a normal situation. And so the groundwater we have is the groundwater that we will have. So recharge and precipitation become those main sources to replenish that resource. If we look at this diagram, what this is showing is, first of all, the percent of the aquifer that is in each of the individual states. So what this is looking at is just looking down from the top, how much land area would be covered, covering the Okolala Aquifer. And so you can see about 36%, almost 37% of the land that is underlain by an aquifer actually is in Nebraska. If you look at the average depth of the saturated thickness of sands and gravels in Nebraska, it's about 340 feet. This is data from 2009. The volume of drainable water that was stored in the aquifer in 1980 was estimated by Virginia McGuire with the USGS to be roughly 2.1 billion acre feet of water. Now, to give you an example, that's about half the volume of water in Lake Michigan. So we have an enormous volume of water that's available to us in the aquifer in Nebraska. In fact, the next column shows that about 66% of the extractable water in the Oklahoma aquifer is actually beneath the soils in Nebraska. So we're very blessed by that resource. When we look at the change, she looked at the change in the amount of water between 1950 and 2007. And so looking at the total decline of water in the state due primarily to pumping irrigation water, what we see here is that we've extracted about 21 million acre-feet of water over that time period. So if we compare the volume that we extracted to the volume that's available, we see that we've used about 1% of the water that's in the aquifer we've actually depleted through irrigation in Nebraska over that time period from about 1950 to 2009. So on a big picture sense, we haven't necessarily, the Oklahoma aquifer is not going dry per se. There's issues in the state, but it's not the entire system going dry. This is a little later study also done by the USGS. And so what they looked at here is just updating the method to 2011. They actually made a few changes in the methodology. So what the different lines here show is the green lines here show the areas, those states where the water level as an average over the whole state has actually increased since 1950. And so you can see that South Dakota and Nebraska are those areas where, in this particular study, the water level actually risen a little bit. The kind of orange-colored bars are those areas where the water level has dropped since that time period. And you can see the primary impact has been in Kansas and Texas. And so 66% of the 66% of the decline has been, 60% of the decline has been in Texas, and about 26% has been in Kansas. And so when you look at the Oklahoma aquifer and you look at what is happening there, you really have to compare the northern in a different light than you would the southern area of the region. Now, I don't mean to say we don't have groundwater management issues in Nebraska. We certainly know that we have issues. Distribution is the key. This map is showing the depth of those sands and gravels that are filled with water in our aquifer. And you can see some areas out in west central Nebraska that saturated thickness is maybe up to 1/4 mile deep. So tremendous resources under the sand hills, a little less as we go across the state then as it pans out. We do know that any time that we irrigate, that water has to come from some source. It can either come from depleting the amount of water stored in the aquifer, or it can come from water that would have made its way to a stream. That's really the two places that you get water from when you pump a well. So what this diagram is showing is that a unconfined aquifer, the original water level was here at what we call the static water level. After we pump for a period of time, the water level drops to what we call the pumping water level. And that slowly drops over time, but after a couple of hours of pumping, that becomes relatively stable. After a few hours of pumping, the water then starts to flow horizontally into the well as we look across this zone. If we look above the water table there on the left, what we see is that before we irrigated, there was water in those sands and gravels above the current pumping level because it was below the initial static water level. When we pumped the well, we dewatered that area just above the water table. And so we get some of our water out of that dewatering and what's often called the cone of depression around the well. But the longer we pump, the more the horizontal flow towards our well becomes a bigger and bigger piece of the water that we need to supply that well. So now we have to think about how does the groundwater interact with our stream flow. And what this is showing on the left is what we call a gaining stream. In this case, the water level in the groundwater is above the water level in the stream, and so that causes water to flow naturally from groundwater into the stream. And so as this flows, you see an increase in the flow in the stream as you go downstream. Now these blue lines that are shown here on the bottom part of this graph represents the elevation of groundwater. And so what you can see is that water is going to flow perpendicular to those lines, and so water is really flowing downhill. So when you have a gaining stream, what you see on the left-hand side is you have kind of an inverted V to those lines above the stream. That means the water is converging and flowing to that stream. On the right-hand side, on this side, we have what we call a losing stream. In this case, the water level in the aquifer is above the elevation of the groundwater. And so water is naturally going to flow downhill, so water flows out of the stream into the groundwater system. In this case, we still have our water level elevation shown here, but now we see that that V is actually upright next to the stream, and so we get a flow of water that's coming away from the stream in those cases. So when we look at water level readings, we're really looking to see, is water flowing into that stream or is water flowing out of that stream? As we go across Nebraska, many areas we have gaining streams, and many areas we'll have losing streams. Some streams or rivers, like the Platte River, is actually in some regions it's a gaining stream. Some areas it's a losing stream. It even changes during the season. Maybe in the spring when we get the rainfalls like we're getting now, maybe those will bring that water level up, and so we get some groundwater flowing into the stream. Maybe late in the season, maybe September, that water then tends to kind of reverse and flow back that other way. The point I want to make here is that there's a strong interaction in a lot of areas of Nebraska between the streams and the groundwater. And that's really what's driving a lot of water resource management and policy, not only in Nebraska, but really all of the western United States today. This is maybe a little different way to look at that. In the upper left-hand corner, we're kind of showing a stream with flow in it. There could be some sediment deposited at the bottom of that stream. That sediment tends to restrict the movement of water from the stream into the groundwater. But what we see is we have a stream on the left, and we have our pumping well is here. As we pump the well, we get this cone of depression that develops. And so if you're really close to the river, you can actually, the cone itself here can actually interact with the water level in the stream on the left. Many times though, after we pump for a period of time, we see this decrease here in the water table in the kind of the static water level over time. And so what you can see then, originally before we began to irrigate, the water level was really at that upper level, and then maybe after we pump for a while, this water level has dropped this amount of distance here over time. And so now there's less head available to cause water to flow to the streams, and so the longer we pump, the less water, that groundwater, will be flowing into those streams in those areas where the streams and the groundwater are connected. We express that by a term we call the stream depletion factor, and what this is showing is we're going to plot on this axis on the bottom the number of years since we started pumping. So if we started pumping a particular well in 1960, and now it's 2015, we pumped that well 55 years. On the left-hand side of the axis, we're looking at what percent of the water that we pumped would have been flow in the stream had we not pumped. And so a kind of a standard that was used for many years was that 28% of the water pumped over a 40-year time period would be kind of a standard to define whether that well was hydrologically connected to the stream. Nebraska recently in the Platte has changed their view of that to look at only 10% and over a 50-year time period. And so what we're doing in the state is we're classifying wells as whether or not they're hydrologically connected or not connected. And those are really used for areas where you need to make adjustments to pumping, and they will have an impact quickly on the river. Now what the lines here show then is the red line shows that if your well was 2 miles away from a stream, it would take about a year before any of the water that you pump would show up as affecting stream flow. After you've pumped maybe for this, let's say here we're at the 50 years, we would be up to about 70% of the water that we pumped out of that well over that time period would be coming from water that would have gotten into the stream. The blue line shows if your well's further away from the stream, maybe 5 miles away, now then we don't really have much impact at all, even for the first 10 years. And by the time we get to this 50-year time period, maybe only 40% of that water we pumped would have been stream flow. The last example would be the green line when we're 10 miles away from the stream in this particular case. No effect, really much effect at all. In fact, it took 50 years to get 10% of the water to come from the stream. And so when we do these of course vary by the characteristics of the aquifer wherever you go, but we're using these to try to look at how we can manage water, get relief to the streams when we need it next to the river, and then how do we manage wells that are further away from the river in that process. So you may read about these or hear about these as you look at NRD or Department of Natural Resource reports, and when they talk about stream depletion factor, this is what they're really looking at. Let's look for a minute then at Nebraska and look at our water balance and how we're going to move forward in trying to look at sustainability. And so what I'm looking at here is I'm taking the average amount of precipitation for the state. So you can see the big blue arrow that's pointing down is, on average, the precipitation in the state of Nebraska is about 22.6 inches per year. We get about 9/10 of an inch of water that flows in from the western side of the state in stream flow that flows into the state. Here we're getting about 2.3 inches of water that flows out of the state in stream flow. Could be in the Platte, could be in the Niobrara, could be in the Republican or the Blues. Okay, so we just kind of add that up for all of those situations. So you can see that we increased stream flow. On the left side there was about 0.9. Here on the eastern side it's about 2.3. So we add about 1.5, almost 1.5 inches equivalent of stream flow from precipitation in the state. Now up here in this upper right-hand corner, we have an area that we call other consumptive use. What we mean by consumptive use is we extract liquid water and we use it in a process that converts that water liquid into a water vapor. Primarily we're using this water to cool, and so a lot of this water is used for cooling of power plants like coal-fired, electrical generation, a little bit in terms of ethanol. And so this is equivalent to about 1.3 inches a year that we're using then for that kind of consumption. But the big piece on this whole diagram is the amount of water that's returning back into the atmosphere as evapotranspiration off of lands in the state of Nebraska. This is water that's transpired through the plants or evaporates directly off the soil or out of a reservoir, and so it's converted again from liquid water into water vapor, so it's a consumptive use. And so what we can see here is about 88% of the precipitation we receive in the state is going back into the atmosphere as ET. Now this water is going to stay in the hydrologic cycle, but the water is not going to stay in the watershed where it evaporated. It's going to be blown primarily to the east with trade winds and our traditional pattern of storms across the state, or the Great Plains. About 6% of the precipitation that we receive is going to go to an increase of of stream flow out of the river. Now the last part I want to look at is the fact that we irrigate. When we irrigate, we increase the amount of evapotranspiration in the field. If we look at the amount of increase in evapotranspiration because we irrigated, we're increasing this, that amount of ET, the amount of consumptive use that we're increasing, is equivalent to about 8% of the annual precipitation. So a lot of us think if we're going to be able to balance this water balance in the state, we're going to have to look at this whole region and not just this bottom line down here looking at that 8% from irrigated agriculture. So we need to move forward in looking at the whole system. So what's driving watersheds in Nebraska, the Great Plains, and the western United States is really this focus on sustainability. This diagram is trying to show all of the different water balances that might occur in an agriculturally dominated watershed. And our primary focus is becoming this amount of water that's flowing out of the watershed in order to meet downstream needs. Those downstream needs could be due to a compact with a neighboring state. It could be for an environmental purpose such as endangered species. But we have an obligation to send some of the water that either flows into our basin or that occurs because of runoff. Some of that water needs to be sent downstream. And of course we fight about how much of that should be shared with our neighbors downstream. But the issue really becomes sustainability. What's driving most of Nebraska right now is really this amount of water that we're looking at in the stream. Now sustainability sounds like an easy thing, but it's quite difficult actually. In fact, it has a stigma. I prefer the idea of sustainable development rather than irrigation sustainability. But some of the questions we have to focus on are shown here in this corner. What do we want to sustain, the ecosystem or the economy? How do we trade off those two? How do we balance upstream versus downstream? Not a lot of good studies looking at how you incorporate the use of groundwater into sustainability. How do you decide on a management time frame? What's our goal going to be? How do you balance a person's property rights against what's good for the community? And then lastly, I'm sure we're going to have to think about an adaptive management procedure. What we mean by adaptive management is that we're going to set some goals, maybe 5 years or 10 years out, and we're going to do things to try to achieve those goals. Now, we're going to be human beings, and we're not going to get it right, and the weather's going to be different than we thought, so we're probably not going to get exactly the right answer. So maybe in 5 or 10 years, after we've worked towards that goal, we need to sit down and reassess that goal, and then we also need to sit down and reassess how we're going to attack that issue. And in a lot of ways, the allocation and the pumping programs that the NRDs and the Department of Natural Resources have implemented are a natural system of adaptive management where they reassess that value at periodic times. Oftentimes it's a 5-year planning horizon. But we have to think about all of these things as a society. All stakeholders have a say in this, and so we really need to think about this idea of sustainability across the basin. We have a lot of opportunities for improvement in the system. Whether it's up here at the watershed level, what could we do different there? What can we do over there on the plant and water use side? And then over on the left, what are we going to be able to do on farm that would have an impact on this water balance? Not only how do we affect the water use, but also how do we affect the value of that water that we are using? I think Nebraska's set themselves up with a system that really encourages innovation that will let us capitalize on that water use. Now we have some issues here. We have to think about differently than we have in the past. We have to start thinking about where's the water go. We have to look at things in a much more interdisciplinary style. And then here at the bottom, we have to begin thinking about better methods for accounting for where the water is being used and where it's going. Some of the methods we've used in the past have served okay, but we need to do a better job of accounting for that water balance in the future. An example of that is if we were going to look at the amount of water that's used for a center pivot, each of the little blue dots and arrows shows a pathway of water after we apply it from our irrigation system where it could go. A significant amount of that water will go up into the atmosphere, either evaporating as droplets or being blown out of the field in what we call drift. Some of it may evaporate off the canopy or off the soil and go as a consumptive use into the atmosphere. Some of the water we apply at a local location may actually run off the field. We also may, if we over-irrigate or we get a wet period of time, we may have some deep percolation in the field. So we have to think about where that water is going in the field. We've done this a lot over time. We need to start thinking about what's going to happen off-field. Some of this water may leave the field either due to natural runoff or due to runoff from irrigation. That water may accumulate in some low areas. We have to think about where does that runoff water go over time. Does it go back into the atmosphere? Does it seep into a stream, into the groundwater, or does it flow into a stream? So we need better tools to be able to account for where this water is actually ultimately going. We can kind of break those into 3 areas. One of those areas would be the water either goes for evaporation, evapotranspiration of the air, it goes to a return flow or a recharge. That is, it either goes into a stream or it goes back into groundwater. And really the only beneficial pattern of water use on this that produces an economic impact is that beneficial consumptive use on the left-hand side there, and that's the transpiration from the crops themselves. That's the one that's related to yield, and that's where we get value. So we're looking at ways, especially to convert from this area here that's evapotranspiration that's not serving much purpose, looking at ways we can either increase recharge or enhance the consumptive beneficial use on the left-hand side as transpiration. We have to manage, we're going to have to start looking at manage our watersheds different than we have in the past. We're going to have to account for where the water goes, and we're working with colleagues to develop some of these tools to help us anticipate and explain that water use. So the issue is that water management is getting much more complex as we go forward. We really need an adaptive management strategy in order to be able to set goals and assess our improvement. And then lastly, we can't just do the same thing we've always done and expect to get a different result. As we're going to expect different results, we're going to have to change some of the things that we're working on. And I would simply say, this has been a cooperative project between a lot of different agencies shown here on the map, and hopefully it's useful to you as you think about water resource management in your location.